Hello there and welcome to a brand new lesson. This is Half Beyond Numbers, where we learn maths the easy way. In this lesson, we are looking at rational functions, and specifically we are looking at the asymptotes and then holes. By the end of this lesson, you should be able to identify vertical, horizontal, and oblique asymptotes. You should be able to distinguish between holes and then vertical asymptotes. You should be able to describe the range by considering restrictions created by these horizontal asymptotes, and then finally to be able to perform complex analysis on rational functions. Here are some basic vocabularies we'll be using as the lesson proceeds, and I'll advise you simply pause and then take a glance before we continue. Without much ado, let's quickly look into it. So let's start by looking at what an asymptote is. When we say an asymptote, it is a line the graph approaches, but it never touches it. It gradually approaches the graph you are talking about. It will try as much as possible to approach this particular line, but it will never touch it. Let's look at what this means. This is a function over here. The blue one is a function 1 over x minus 3. So this 1 over x minus 3, you realize that if you take this aspect of it, it is trying to approach this line we see over here. It is gradually trying to approach this yellow line, but yet it doesn't touch it. Even if we proceed and then we go, you realize that it will still never touch it. If I'm to zoom for it to see, you see, if you are looking at it from afar, you think it is actually touching it, but then it is not. You see, that is it. So we call it what? We call this particular line the asymptote. Now there are types of it. We have the vertical, the horizontal, and the oblique one. So let's start by looking at the vertical asymptote. So talking of the vertical asymptote, for a rational function r of x, which is giving us a p of x over a k of x, you see. So we get the vertical asymptote when the denominator is equal to 0. So that is if k of x is equal to 0. An example is what you see over here. So this is the function 1 over x minus 3. You see. Now, at q of x, that is the denominator, equals 0, we would have x minus 3 is equal to 0. And that implies that x is equal to 3. So if you look at this graph of 1 over x plus 3, you realize that the blue line up here on this first quadrant does not touch the line x equals 3. This one also does not touch this line x equals 3. They try as much as possible to increase their values, but then they will never touch it. Both when moving upwards and then downwards, they never touch their line. The reason being that it doesn't exist, or it is undefined. The function is undefined at that particular point. You see. But when we talk of the horizontal asymptote, so talking of the horizontal asymptote, it exists if there is this horizontal line that the function tries to approach to it. You see, as the x value increases. To obtain that, we usually compare the degrees of the numerator and then the denominator. We'll look at more examples on that, but graphically, this is how it looks like. So you see this particular line over here. We have the function that is trying to get to it, but then it doesn't get to it. Then we have the last one we call the oblique asymptote. So the last one we'll be looking at is when the asymptote is oblique. When we say it is oblique or slanted, it is usually when the degree of the numerator is 1 more than the degree of the denominator. So for instance, if you have your rational function r of x being, let's say, an x squared plus 1 all over x, realize that the degree here is 1 more than that we have over here. Usually these ones give us oblique asymptote. So these are the 3 types of asymptote we might we'll be solving questions on in this lesson. So with all that we have said so far, let's look at a quick summary of it. There is a vertical asymptote if q of x, that is the denominator, equals 0. That is after you have cancelled out your necessary factors. So just as we did for the previous one, you equate the denominator to 0 and then find its zeros. That becomes your vertical asymptote. But then for the horizontal, when the degree of the numerator is less than the degree of the denominator, then it has a horizontal asymptote of what? Y equals 0. Anytime that degree, that is that of the numerator, is less than that of the denominator, it has this as its horizontal asymptote. On the other hand, now when we come to the horizontal asymptote, there are two cases. First of all, if the degree of the numerator is less than the degree of the denominator, anytime you have that happening, then your asymptote is simply y equals 0. Anytime. So you'd always go and then check for the degrees. If the degree of the numerator is less than that of the denominator, y equals 0. As simple as that. But then if the degree of the numerator equal to the degree of the denominator, then we obtain the asymptote as what? Y equals the coefficient of the numerator, that is the leading coefficient of the numerator, over the leading coefficient of the denominator. That equation becomes your what? The equation of the horizontal asymptote. Then the third case, that is when we have no horizontal asymptote at all. That is when the degree of the numerator is greater than the degree of the denominator. It is not a horizontal asymptote. Then we come to oblique asymptote, that is the slanted one. So the slanted one occurs when the degree of the numerator is equal to the degree of the denominator plus 1. The degree of the denominator plus 1. If you're able to obtain, or if you're able to verify that, then you can now come and then solve that equation using what? An equation of a line. Our next item we want to talk about is the holes, or the removable discontinuity. If you look at this equation we have here, that is this function I have represented graphically. If you look at this function I have represented graphically here, you realize that this is a straight line, right? But even though it is a straight line, there is something happening at this particular point. The function is not continuous at this point. There is a hole there. Do you see? If I'm to zoom in, you realize that there is a hole over here. There's no space. The line is discontinuous. This is what we call the hole. So this becomes the hole. Now, the hole is sometimes confused with the asymptote, that is the vertical asymptote. So let's say you have, most of the times if you want the asymptote, what we do is, if you have a rational function, r of x, which is equal to, let's say, a p of x all over a q of x. Now, if you're able to factorize p of x to be x minus a and then x minus b, and it happens that the denominator is also an x minus a. Now you realize that this particular one would have been your vertical asymptote. You see, because all you would have done is x minus a equals what? 0. Then you say x equals a becomes your vertical asymptote. But looking at it carefully, you realize that this one would cancel this. You see, so in that case, it no more becomes a vertical asymptote because it is not even in the domain. Do you see? So we say it is a hole and not a vertical asymptote. But on the other hand, If you had our numerator to be if you had our numerator to be x minus b, then x minus c all over an x minus a. This one here does not cancel anything, you see. So with that, you can say your x equals a is a vertical asymptote and not a hole, you see. So the holes are those that would actually cancel out, and the vertical asymptotes are those that will not cancel at the end of the day. We would best understand these concepts if we take some questions and then solve. So let's quickly look at some questions under all that we have spoken about so far. So this is our first question here, and it says for f of x, so we have f of x which is equal to 3 over x minus 5. So first of all, we have to find the vertical asymptote, and then secondly, we have to find the horizontal asymptote. So let's start with the vertical asymptote. So for vertical asymptote, we said for the vertical asymptote, that is where we'll check for the denominator being equal to 0. You see, so let's just call it VA. So for VA, then the denominator, which is scale of x, is equated to 0. In this case, there's nothing to factorize. You see, so we just go straight forward. That is to say, x minus 5 is equal to 0. Making x the subject, we have our x, which is equal to what? 5. So the vertical asymptote is simply the line x equals 5. The function we are talking about or we are working on is what I have represented over here. And if you look at it critically, this is the line x equals 5. So the function tries as much as possible to move close to it without touching it. Hence, it is our vertical asymptote. Now for the second one, which is B, it says we want the horizontal asymptote. So it is the horizontal asymptote that we now compare the degrees. You see, so you said if the degree of the numerator is less than the denominator, then the horizontal asymptote is y equals 0. If the degree of the numerator is equal to that of the denominator, then it is y equals the coefficient of the numerator divided by the coefficient of the denominator. But then if the degree of the numerator is more than the degree of the denominator, it has no horizontal asymptote. So that is what we are coming to do here. For horizontal asymptote, as we can see, the function can be rewritten as 3x to the power 0 all over x minus 5. And as you can see here, the degree is 0. And the degree we have here is 1. You see? So we can conclude that since the degree, so the degree of the numerator, let's call it p of x, is less than the degree of k of x, then it simply implies our horizontal asymptote is the line y equals 0. So it's just about you understanding the concept and then looking at what we have to do our comparison and then determine your asymptote. That is all. So graphically, this is the horizontal line we are talking about over here. This is the vertical asymptote. This is the horizontal asymptote. Very, very simple. That is all for this particular question. Let's solve some few more. So our second question we have here says g of x is given as x minus 2 all over x squared minus x minus 6. You have to find the vertical asymptote, the holes, and the horizontal asymptote. So we have g of x equals x minus 2 all over x squared minus x minus 6. If we want our vertical asymptote, we know that we first of all need to confirm if there is anything to cancel out, you see. So we can rewrite the function, that is using the method of factorization. We have what? X minus 2 all over x squared minus x minus 6 when factorized gives us an x minus 3, and then an x plus 2. You realize that there's nothing we can cancel out. You see, this is a plus 2 and this is a minus 2, so it can't be cancelled out. Now, if there's nothing to cancel out, then that is to tell us that there are no holes. There are no holes at all. So first of all, we can say there are there are no holes. If there are no holes, let's go on and then we solve for the vertical asymptote. So for the vertical asymptote, we said we would have to equate the denominator to 0. So VA, we have x minus 3, then the x plus 2 being equated to 0. For this first one, we have x minus 3, which is equal to 0. Hence, our x equals 3. And then for the second one, we have x plus 2, which is equal to 0. And then x equals negative 2. You see, so these are the vertical asymptotes we have. And if you look at our graph we have over here, this line we have over all this whole thing, that is the blue one all together, is this graph we have here, right? It is this function we have over here. Now, if you look at all the blue lines, you realize that this particular one goes downwards and then tries as much as possible to touch this line. This line is negative 2, x equals negative 2, but then it doesn't touch it. For this particular one, it moves upwards, but then it does not touch this line. Then the same thing applies here. That is for x equals 3. So these are the two vertical asymptotes. But then for the horizontal, we said for the horizontal, what we do is we compare. So first of all, let's compare. Looking at the degree of the numerator, it is less than the degree of the denominator. You see, so it is always easy to tell. So we say since the degree of p of x is less than the degree of q of x, then it simply implies that our horizontal asymptote is simply y equals 0. And that is what you have over here. So if I'm to move to the right hand side, you realize that it continues without touching our line y equals 0. That is the x-axis. And if I move to the left hand side, you'd also notice that it continues without touching the line y equals 0, or the x-axis. You see, so once again, we have to stick to the rules and then we solve accordingly. And you realize that it is very, very easy. We have our third question here, and it says, for h of x, which is equal to x squared minus 4 all over x minus 2, we have to identify the holes or the asymptotes. That is, depending on your analysis, you'd have to tell us whether or not they are holes or whatever it is. So we have our h of x, which is equal to x squared minus 4 all over x minus 2. This is what we have. So if we want to determine whether or not they are asymptotes, then we just equate the denominator to be equal to what? 0. But then looking at what we have, the numerator can be factorized. So if you have to factorize the numerator, this is difference of two squares. So it is x minus 2 and then x plus 2 all over x minus 2. You see, so with that, this cancels out this and we'll be left with what? X plus 2. Now this we have is a straight line. You see, so if you are to get this on a function, it is as you see down here on our graph. But then if we come back to the function itself, we have x minus 2 as the denominator. So if you want to substitute and then you substitute x minus 2, you know, for fractions, if you have a denominator being 0, it is undefined. So there is a hole over there, you see. So the line doesn't just continue straight. Right here, if I'm to zoom in, you realize that It is not continuous. There is a hole, there is a gap in here, and it is caused by we substituting x to be what? 2. So that 2 minus 2 gives us 0. You see? So with that, if you are to solve just as you do, so for k of x equals 0, where we have our k of x being x minus 2 equals 0, then we have x being equal to what? 2. We don't call this an asymptote. No, you rather call it a hole. Now, since it is a hole in the line, then let's look for its corresponding y value so that we complete and then we get it as a coordinate. So for now, we know our h of x was given as what? Our h of x is x plus 2. So substituting it, we have what? 2 plus 2. That is the x for this 2 over here. We have 2 plus 2, and 2 plus 2 gives us a 4. So that is to say the particular position where we have the hole is what? 2, 4. That is the x coordinates. The x is 2, and then the y is what? 4. As simple as that. Now, if you wanted to verify whether or not there is a vertical asymptote, then we know for the vertical, all we do is we compare the degrees. Now, the degree of the numerator is 2, and then the degree of the denominator is 1. And we said if the degree of the numerator is greater than the degree of the denominator, then it has no vertical asymptote. As a quick revision, this is what we are talking about. You see, if the degree is less, then you have what? The asymptote being y equals 0. If that of the numerator is more than that of the denominator, there is no horizontal asymptote. And then if they are the same, that is where we say y equals the coefficient of the numerator, that is the leading coefficient of the numerator over the leading coefficient of the denominator. So that is all for this question. That is question number 3. Let's solve 2 more questions that will test our understanding on 2 different concepts. And then we can end this lesson. So this is our 4th question. And what do we have? It says we have to find all the asymptotes and zeros of f of x equals 2x squared minus 8 all over x squared minus 9. So our function f of x is given as well 2x squared minus 8 all over the x squared minus 9. So looking at what we have, it is obvious we can do some factorization. So for the numerator, for instance, we have 2 into bracket and x squared minus 4 all over the x squared minus 9. Where do we get our x squared minus 4 from? You know, this, the coefficient of x squared we have here, and then 8 have common factors, you see. So their common factor is 2. The reason why we are doing that is we have identified there is a difference of 2 squares somewhere around here. So we want to evaluate that. So evaluating a difference of 2 squares, it is actually a 2 into bracket. This we have here is an x squared minus 2 squared, you see. So we evaluate that, and then this we have here is also an x squared minus 3 squared. So using our idea on difference of 2 squares, we have x minus 2 and then an x plus 2 all over. We have x squared minus 3 squared giving us x minus 3 in one bracket, and then an x plus 3 also in the other bracket. So now let's look at how this is going to help us to get our zeros and then our asymptote. For the zeros, all we need to do is to equate the numerator. So the numerator, let's call it p of x. So let's equate the numerator to 0. You know, a fraction or a polynomial or a rational function specifically is 0 if the numerator is 0. Hence, we equate this numerator, which is 2 into bracket, the x minus 2, and then x plus 2, we equate them to 0. 2 cannot be equal to 0. You see, so for the 2, it is out. So to get our zeros, we equate the two brackets to 0. The first one being x minus 2 equals 0. And x is obviously 2. Then the second one being x plus 2 is 0. And x is also obviously what? A negative 2. So we can conclude by saying the zeros of this particular rational function is x equals 2 and then x equals negative 2. When we come to the asymptotes, you realize that this time around there's nothing to cancel out. You see? So first of all, let's look at the vertical asymptote first. So for vertical asymptote, you remember that we said for vertical asymptote, one of the conditions is if the degree of the numerator is the same as the degree of the denominator, then it is given as y equals the coefficient of the leading coefficient of the numerator, which in this case is 2. So 2 over, this is the leading coefficient. The leading coefficient is simply the coefficient of the variable with the highest degree. So over the leading coefficient of the denominator. In this case, it is what? 1. So 1. And evaluating it, it simply means our vertical asymptote is simply y equals 2. As simple as that. Then we come to the horizontal asymptote. So for the horizontal, that has to do with the denominator. So we would have to equate x minus 3 and then x plus 3 to what? 0. So you equate them to 0 and then solve for our x values. Equating these brackets to 0, we have x minus 3 is equal to 0. And our x is simply what? A 3. Then x plus 3 is equal to 0. And x is what? A negative 3. So for our horizontal asymptote, we have what? The line x equals 3 and then x equals negative 3. And for our vertical asymptote, we have the line y equals what? 2. And for our zeros, we have what? X equals 2 and x equals negative 2. Now let me quickly get that on the graph for you. This is actually the graph we have here. You see how it looks like. Very, very nice. It's a nice graph. So with this, graphically, you would see the roots over here. You know, the root is simply where the y values are 0. So this particular point, that is x being negative 2, which we have solved and then confirmed, and then x being 2, which we have also solved and confirmed. Now let's look at vertical asymptote or the horizontal. Let's first of all try that of the vertical. So you said for the vertical asymptote, what do we have to do? We look for the values of the denominator that give us 0. That is after we cancel. For this particular function we have here, there is nothing like cancellation because there are no common factors. You see, so the only thing we can do now is to equate x minus 3 and then x plus 3 to 0. Then you solve for each bracket. For the first bracket, if you have x minus 3 being equal to 0, then it simply implies your x is equal to 3. Then for the second one, if you have x plus 3 also equals 0, then your x is also equal to negative 3. So these are the two lines, or let me say, these are the two vertical lines that our function is trying to get to, but it will never get to. So graphically, we have them here, these two lines. So you see, for this particular section of the function, it goes up and then tries to touch this green line, but it doesn't. The same way for this particular section as well, it goes down and tries to touch, but then it doesn't happen. Same for what we have here as well. So it goes up even to infinity, but then it never touches this particular point, and then it goes down as well, and then it never touches. So these are our vertical, the equation of our vertical asymptotes, and then this on the other hand is the zeros. Now, is it possible that there is a horizontal asymptote? Let's verify that. So you said for the horizontal asymptote, what happens is you'd always compare the degree of the numerator and that of the denominator. We said if that of the numerator is less than that of the denominator, then it is y equals 0. If they are equal, then it is y equals the leading coefficient of the numerator. In this case, it is a 2 over the leading coefficient of the denominator, which is 1. And that gives us a y is equal to 2. So our vertical asymptote of this rational function is the line y equals 2. Graphically, you see it over here. So the same way, this tries to get close to this particular line, and then it doesn't touch it. This also tries, but then it doesn't also touch it as well. And this also just turns around it over here, as you see. You see. So these are all the asymptotes of this particular function and the zeros as well. The last question will be a problem for you to solve. So I'll give you some few minutes. You try on your own, and then you quickly come, and then we do it together. So for our last question we have here, is that you have to analyze the function f of x. And f of x is x squared plus x minus 6 all over x squared minus 5x plus 6. Analyze it completely. So you have to tell us the holes, the vertical asymptote, and then the horizontal ones, the zeros, and the y-intercept as well. So first of all, let's start with the holes. So for the holes, before we even do that, let's factorize our function. So we've gone through all of factorization, hence I'll just quickly write what we have here. So factorizing our numerator, we know the factors of -6, that will give us 1, 3, and -2. So if you factorize it, since the coefficient of x squared is 1, we have x, then minus 2, then times the x plus 3, all over, for the denominator, the factor pairs of 6, and then the factor pairs of 6 that adds to give us -5 and -3 and -2. So we have our x minus 3 and then the x minus 2. If you want to simplify further, then we are going to get our f of x being equal to this here cancels out this, so that we are left with what? An x plus 3 over x minus 3. So with this, let's solve for our holes. So we usually obtain our holes from the cancelled terms, you see. So to get our holes, all we are going to say is x minus 2, that is the cancelled terms, equals 0, making x the subject, our x is equal to 2. Then we find the value of the function at x equals 2. So that is to say f of 2 will be equal to, we substitute it into this function. If you substitute it into this function, you are going to get an error. Hence, into this function, we have 2 plus 3 all over 2 minus 3. And when that is evaluated, we have a 5 over -1. 5 over -1 simply gives us a -5. So we say it implies that the coordinate of the hole is what? 2, -5. So with that, if I'm to zoom in and then we take a look at the function, you realize that at x equals 2 and y equals -5, there is a hole here. The function ceases to continue. It is discontinuous at this point. is what we call the whole. So with the whole done, let's then look at the asymptote. Or even before the asymptote, we can quickly go to the zeros. So for the zeros of a function, or for this case, a rational function, then we have to equate the numerators to what? 0. So that is to say, our numerator, which is x minus 2, we want to use the factorized form. So x minus 2, then x plus 3 should be equal to 0. Equating both brackets to 0, you are going to get your x equals 2, and then x equals negative 3. These are the points on the graph where our function gives us what? 0. Now, to solve for the zeros, since our f of x is now equal to this here, x plus 3 over x minus 3, we use the numerator. So for the zeros of a function, then the zeros of a rational function, then the numerator has to be equal to 0. So that is to say x plus 3 equals 0. Making x the subject, we have our x, which is equal to what? Negative 3. So at x equals negative 3, the function is 0. Or in other words, this is the x-intercept of the function. If I come here, you realize that the function cuts the x-axis, or it crosses the x-axis at x equals negative 3. Very simple as well, isn't it? Then we come to the y-intercept. So the y-intercept is usually where we have our x equals 0. You see? So at y-intercept, what happens? Y, or x rather, is equal to 0. So we would evaluate the function at what? 0. And that is to say 0 plus 3 all over 0 minus 3. This gives us a 3 over negative 3. Hence, our f of 0 is what? Negative 1. So the y-intercept is at what? 0, negative 1. Let's come to the graph to confirm that this is our y-intercept. Now let's look at its coordinates. You see, so at x equals 0, and then at y equals negative 1. As you see the negative 1 over there very nicely. So that will be it for our holes, zeros, and then intercept. Let's now look at the vertical and then the horizontal asymptotes. So for the vertical asymptote, it is usually where we have a function being equated to 0. And remember, we had f of x being equal to x minus 3 over x plus 3. X plus 3 over the minus 3. So for our vertical asymptote, what we are going to do is we equate the denominator to 0. That is to say x minus 3 should give us what we have here. And making the x the subject, we have x being equal to 3. This is our vertical asymptote. So if we come right here on our graph, you would see that shown here. So you see this straight line over here. The function tries as much as possible to touch it, but then it doesn't touch. On both sides, both upwards and then downwards. It tries as much as possible, but then it does not touch. Then we come to the horizontal asymptote. So for the horizontal asymptote, we have what? That is where we look at the degree. The degree of x is 1. That is, the degree of the numerator is 1. And then the degree of the denominator is also 1. And we said if the degrees are the same, then it is simply y equals the leading coefficient of the numerator, which in this case is 1, over the leading coefficient of the denominator, which is also 1. And this one simplified gives us y equals 1. This is our horizontal asymptote. So on our graph, that is what I have represented with this line over here. The graph tries as much as possible to reach it, but it doesn't touch, and then same applies over here. So this is the full analysis of this particular question we have over here. I do hope you are able to do that on your own. That ends our examples for this session, and I do want to believe that you are able to grasp and you'd be able to move further to solve questions without even being guided. As usual, I'll leave it some exercises so you try on your own. So here are 5 questions you can try on your own just to test your understanding. They are all based on what we've done so far in this lesson. If there's any issue of concern, you can always let me know in the comment section. When notified, I'll address that for you. If this is your first time on this channel and you do think it will be of help to you, you can choose to subscribe if you so do wish, so that anytime I release a video, you'll be notified, and then you can also come and then learn with us. See you in our next lesson. Bye for now and do stay safe.